How's it going, ladies and gentlemen? Mr. Donahue here with some 13.5 and 6 problems, colligative properties, and colloids. All right, so looking at the first question, it says a 0.1 mole solution of which one of the following solutes will have the highest vapor pressure? So if we're talking about highest vapor pressure, we got to think about, well, what happens when we dissolve stuff into solution? All right, this is what you can think of. All right, so we got particles that in the liquid phase that want to become a gas and cause vapor pressure, right? You're going to create an equilibrium there. And if you're dissolving stuff in that water, well, now the water is going to interact with it and be attracted to it, which is going to hold it in solution. So as you increase the amount of solute, the vapor pressure goes down. So if we're talking about the highest vapor pressure, we want to have the least effect. So it's saying they're all 1 mole or 0.1 mole solutions. So what's going to be different between them? Well, you got to look at most of these are ionic compounds. So when they dissolve, they break apart into more than one particle. For example, KClO4 is going to break up into K plus and ClO4 minus. So even though it's 0.1 mole for that compound, effectively it's twice as much because it breaks apart into 2 particles. So you would really have a 0.2 mole concentration of particles. All right, so we're going to take a look at that. KClO4 is going to break up into 2 particles. CaClO4 2 is going to break up into 3. This one's going to break up into 4. Sucrose is covalent. It's molecular, so it's not going to break apart. It's going to stay as 1 particle. And NaCl is going to break up into 2. So which one of these have the highest vapor pressure? The one with the least effect, which would be sucrose. 21. As the concentration of a solute in a solution increases, the freezing point of the solution blank and the vapor pressure blank. All right, so going back to my model of what's going on. All right, so we have some liquid particles in liquid phase, right? So if they were to freeze, you know, they become really, really structured and organized and arranged nice and neat. And I'm not going to finish drawing that because you guys get it. All right. So if we were to add more stuff in there for it to interact with, well, what's that going to do? Well, those particles are going to have a harder time becoming more organized like that because you have this stuff in the way that's messing it up, keeping it messy. So in order to get this organized, you got to get lower. So as you dissolve stuff, the freezing point goes down. And just like I mentioned in the last problem, the vapor pressure would also go down. So 21 should be choice D. They both decrease. 22, which of the following liquids will have the highest freezing point? All right, so first question is, well, what effect does it dissolving stuff have on the freezing point, which we just kind of covered in the last problem. The freezing point goes down, right? So as you dissolve stuff, the freezing point drops. So if you're talking about the highest freezing point, you want the least affected. Which one of these things is going to have the least effect? Well, pure water is going to be pure, right? There's no effect. There's no freezing point depression when it's pure water. Right, so that would have the highest freezing point. 23. Which of the following aqueous solutions will have the highest boiling point? So now we're dealing with a new property, boiling point. Well, as you dissolve stuff, the boiling point goes up. I picture like a thermometer. And if this is my boiling point and this is my freezing point, this gap gets bigger. The freezing point drops and gets lower, and the boiling point goes up as you dissolve stuff. So highest boiling point would be the most effect. Which one has the most effect? Well, they give us the concentrations and they also tell us what it is. Now remember back to the other problem, we have to look at how many particles does it break up into. Na2SO4 is going to break up into 3 particles. So if it's 0.1 for the whole thing, you got to times that by 3, and you'd really have 0.3 mole of particles. Glucose is going to stay together. It's going to be 0.2. Sucrose, same deal, 0.25. NaCl is going to break up into two particles, so it's going to be 0.2 molal, and SrSO4 is also going to break up into two particles, so it will be 0.2 molal as well. So which one's going to have the most effect? One with the highest concentration of stuff, so it would be A. 24. What is the freezing point of a solution prepared by dissolving 11.3 grams of calcium nitrate in 115 grams of water? It gives you the molal freezing point. So hopefully you guys are like, oh, hey, I know of an equation. Delta T equals that constant times the molality, right? But what is this the molality of? It's the molality of the particles, right? So it could be expressed equals Kf times the molality, number of particles, the Van Hoff factor, the number of particles that it breaks up into. So if we're looking at calcium nitrate, it's really 3 times that. It breaks up into 3 particles. All right, so what's our plan going to be? First step is going to be, we're going to have to figure out the freezing point depression, right? And in order to do that, we need to know the molality. All right, once we have the molality, then we can plug it in and solve for delta T. 2, 1 and then 2, John. All right, so once we have the delta T, we got to go, all right, well, it's freezing point depression, so it's 1 minus the delta T, and that'll give us our freezing point. All right, so first step, got to figure out molality. Delta T equals Kf. Actually, I'm going to do the math in one step. I'll show you how. Times the molality, which is the same thing as saying Kf times moles over kilograms of solvent. All right, so let's plug in what we know. Kf is 1.86 degrees Celsius per molal times by, well, how do we get moles? We'd have to do 11.3 divided by the GFM of that, which they give us is 164. So that's moles over kilogram of solvent, 0.115 kilograms. And remember, we'd have to times that all by 3 because of the Van Hoff factor that it breaks up into 3 particles. And you get a delta T of 3.33. So last step, it's just 0 minus 3.33, and you get negative 3.33 degrees Celsius. Best answer there would be A. All right. 25. A solution containing 10 grams of an unknown liquid and 90 grams of water has a freezing point of blank. Given the K off of that, what is the molar mass of the unknown liquid? All right, well, I know this formula, and I know molality is moles per kilogram solvent. All right, so what's my steps going to be? Your first step that you're going to have to do is you're going to have to solve for molality. All right, once you have the molality, you can solve for moles. Now, once you have moles, you also know the mass that you used. So the last step would be just the 10 grams divided by however many moles that you found it, and that'll be the GFM. All right, so 1. Solve for molality. Molality is going to equal delta T over Kf. All right. You know what? This is what we're going to do. I'm going to do it all on one big problem and show you how it's better. So we know delta T equals Kf times the molality, right? So we also know that this molality can be expressed as moles per kilogram of solvent. We also know, hey, how are we going to solve for moles? It's a good question. I forgot. No, but moles is really the same thing as what? It's grams over the GFM will give you moles, right? So let me just plug that in up here. And now I have one equation where the only thing I don't know is the thing I'm trying to solve for. They told me the delta T, they gave me the KF, they gave me grams of solvent and whatnot. They gave me the grams of the solute. So now I just got to rearrange this to give me the GFM. And that's just some algebra skills. Right, and now you just plug in all the numbers at once, which in my opinion is a lot easier than writing stuff down, rounding, and then doing all that nonsense. So it'd be 10.0 over the delta T, which would be 3.33, and that's all over the kilograms of solvent, 0.090 kilograms, and you get the answer being 62.1, choice E. That's it. 26. Solution is prepared by dissolving 6 grams of an unknown non-electrolyte in enough water to make 1 liter of solution. The osmotic pressure of this solution is 0.75 atmospheres at that temperature. What is the molecular weight? All right, well, first thing to call upon is the formula for osmotic pressure. And there it is. All right, well, they gave me grams. They told me the osmotic pressure. R is a constant. T they gave me. And V they gave me. So it looks like right off the bat I can solve for N, but they don't want N. They want the molecular weight. So I got to think of another equation where N is involved. N is also equal to the grams over the GFM. And hey, look, they gave me the grams. They're asking me for the GFM. I can solve for N. So the first step is going to be solve for moles, right, using this equation right here. All right, second step would then be to do the 6.00 grams over the number of moles, right? But I'm a bigger fan of doing all the algebra at once. So I'm going to combine those equations into one equation. So then I don't have to keep rounding and stuff, and I can just plug it into the calculator all at once, right? So now the only thing I'm solving for is GFM. I rearrange, I get GFM equals grams over the osmotic pressure all over volume in liters times RT, which equals, let me find my math, 6.00 all over 0.750 all over 1 liter times R, 0.08206 times the temperature in Kelvin, 298. And you will get an answer of 196, which is choice B, as in Bravo. All right. 27. Vapor pressure of water at 25 degrees Celsius, 23.8 torr. Determine the vapor pressure of water at that temperature in a solution prepared by dissolving 21 grams of urea, a non-volatile, non-electrolyte with that GFM, in 75 grams of water. All right. First step, well, what are they asking? I think they're asking for the partial pressure. So I know a formula there. I'll go forward. Right, where this is the actual vapor pressure, this is the standard vapor pressure, and that XA is the mole fraction. All right, well, let's figure it out. They want to solve for the pressure. They tell us the standard pressure for pure water. So first step is we're going to have to solve for XA, right? We're going to have to solve for the mole fraction. Well, how do we go about doing that? Good question. Brain fart. So first thing that you got to do is they tell you grams. So you got to go from grams to moles because the formula for the mole fraction is moles of whatever you're looking at over moles total, right? So first step, 21 grams divided by the GFM, which they give us 60. 21 divided by 60 equals 0.35. moles of urea. Now we also got to find the moles total. So we got to go, all right, well, what's the moles of the water? So we have 75 grams of it divided by its GFM of 18, and we get 4.17 moles of H2O. So combine those, and what do you get? You get a total of 4.52 moles. So XA is going to be equal to 0.35 all over 4.52. All right, did I do that right? Oh, no. My bad, guys. My bad. It's not 0.35. Why isn't it 0.35? Because we're trying to find the vapor pressure of water. So we want the moles of water. So it'll be 4.17. Right, this A is the mole fraction of water that we got to use. So it's 4.17 over 4.52, and we get a mole fraction of 0.923. So now we can plug it into that equation. PA equals 0.923 times by the standard pressure, vapor pressure that it should be, 23.8. And you get 22 torr, which would be choice C. All right. 28. The osmotic pressure of a solution is formed by dissolving this much in that much water. Well, let's take a look again. P H2O is going to have to equal the mole fraction of H2O times the standard H2O. All right, so first step again is going to be, solve for moles. It's just kind of like the last problem, right? So I know the osmotic pressure. Oh, my bad, guys. Ignore all this. I'm still in last problem mindset. My bad. My apologies. Stop yelling. All right, restart. Osmotic pressure equals the moles over liters times RT. All right. All right, well, they tell us milligrams, and they tell us liters, and they tell us temperature, and they want the pressure. So we just kind of do some plugging and chugging. Right, so how do we get moles? Well, we got to divide grams. So if they give me milligrams, I got to convert to grams, and then divide that by the GFM, which is 180.2. And that is our moles. That is that. Divided by the liters, 0.250 liters times R, 0.08206, because we're using the atmospheres, and times by the temperature in Kelvin, 298. And we get an osmotic pressure of 0.0136, which would be choice C. All right, and this last one is just kind of a, did you read the section that you're supposed to about this stuff? You'd be able to identify which one of these things is not a colloid, and it would be choice C. A homogeneous mixture is not a colloid. All right, so a lot of math in that section. I hope it wasn't too overwhelming. Rewatch, bring in questions, see you in class.